Welcome everybody. My name is Schmalstieg, and I will start this tutorial, and I should share my screen. Let me see if I can get that up and running. Okay. Skip share. I wanted it with audio. So, okay. Can you see my screen?
Yes.
Okay. Great. Well, I guess then we're all set. So I'll also keep the chat window open. I think the group is not so large, so we can also have audio questions, but of course, feel free to use the chat, and I hope I notice that in a timely manner. The tutorial is about a brand new system which we are releasing. You can see with me my co-author, co-developer, Philipp Fleck. So we're both from Graz University of Technology, and RagRug is our joint work. It's also a PhD project of Phil. And it is a toolkit for situated analytics. And slide. So we have a 90-minute time slot today in order to tell you about the concepts and the design rationale, and also some hands-on information about RagRug. I will start talking about concepts and design rationale roughly in the first half of this presentation, and then Phil will talk about at least two of the examples that we have been working on, and then hopefully there will still be some time for Q&A. And this toolkit is actually, we're making it available as open source. So as it's custom now, there's a GitHub page that you see on the bottom here. And this is where you can find all the code and also video material and the very recent preprint of the TVCG paper that has just been accepted. So this is, there is a paper, but it's forthcoming in TVCG. It will give you all the details, and it was just accepted in time before the tutorial deadline of VR. So we are able to talk about it now, which is a great opportunity. Okay, so again, feel free to interrupt me at any time if there's something unclear or needs to be discussed. I'll start by jumping way back to what is now 30 years in the past, when I was really starting out doing VR and AR stuff. And at that time around, there were new projects coming up. For example, the virtual wind tunnel, a seminal VR work done by Steve Bryson at NASA. I'm not sure how many of you remember this work, but it was definitely very impressive at the time. It was one of the first explorations of flow data, in this case aerodynamics of the space shuttle. And back in those days, they had to build their own immersive display, right? It was this arm-mounted display called a BOOM, a binocular omni-oriented monitor, which had integrated mechanical tracking and such, and then of course was driven by the expensive graphics workstations at the time, which only NASA owned. And as a PhD student, I was only dreaming of that kind of stuff. But it could be called one of the early explorations of immersive analytics. Now we call this immersive analytics, the interactive visualization of abstract data combined with not a conventional desktop computer, but with an immersive medium. So either virtual reality, which is what it was then, or alternatively augmented reality, anything along the mixed reality continuum. You know, that idea is 30 years old, but of course today we can go and buy an Oculus Quest, let's say. As a matter of fact, I have it here right in front of me. It's my home equipment. And with a fraction of the cost, we can do really compelling immersive analytics problems. And this is why I believe this is now will open up a new trend. And in fact, we see more and more papers, research works, also practical systems coming out. And I would like to make the distinction between immersive analytics and situated analytics here, because the talk is actually about situated analytics. So what's the difference? Well, as always, it's a subtle thing, and I don't want to get stuck in definitions, but the general idea of immersive analytics is that the visualizations are transported into an immersive medium, whereas in situated analytics, the visualizations, interactive visualizations, are transported into a medium that is somehow grounded in reality. So that points us towards augmented reality as a mode of delivery. Yeah? Although there could potentially be other modes, and this is where the debate starts, of course. But in that sense, situated analytics is more than immersive analytics, right? It builds on the strengths of immersive analytics. It takes away this purely virtual, sort of disturbance-free aspect, but in favor of linking the analytics to the real world and grounding it in reality. And the best distinction is actually proposed in the paper by Wesley Willett and his co-authors, where they say situated visualizations, situated analytics means in perceptual, the term situated means in perceptual proximity to a physical referent. And this notion of a referent is something that is really important here, because that's something we don't have in VR or in immersive analytics, right? A referent is a meaningful physical object which is somehow perceptually close to the user. So if you look at an X-ray visualization in augmented reality of cables buried in a wall, showing you where to drill, right? This kind of X-ray visualization, then we should call that situated. Whereas if on the same wall we put a web page or a chart of product sales, it has no meaningful connection to the wall. Therefore, it's not situated. So all these like advertising videos for the HoloLens where they put web pages on the wall, it's all nice and good, but I wouldn't call that a situated visualization. We can distinguish at least two flavors of reference. That's something that is not much discussed. The generic reference will typically be passive objects, just things in our environment, but then we can also have active reference, which somehow communicate electronically to us. And in particular, we'll talk about objects that are connected to the Internet of Things, because this is obviously the up and coming massive disruption that will be happening already. Everything that has electronics today has a microcontroller embedded, and it's only a matter of time until it will all be networked, right? So this is why situated analytics is important to visualize information related to physical reference, and in particular, these active reference. And this is what we will talk about. And RagRug is our attempt at forming a toolkit that lets you build situated analytics applications, in particular using augmented reality. And when I talk about situated visualization, situated analytics, and there's any sort of visualization experts in the audience, I really always have to emphasize it doesn't break new ground concerning the kinds of visualizations it delivers. Right? It extends existing immersive analytics tools, and we'll see what that is. But it does break new ground concerning reference, because it supports both passive and active reference and visualization authoring involving those references. And now is the time. I'll just stop the screen sharing and restart this with video optimization, so we have the best possible playback, because I don't know how fast that is. Yeah, let me share my screen with optimize for video, and I hope this works fine for you now, because it also has sound.
We present RagRug, a toolkit for situated analytics. Smart fridge. We installed a thermometer and a distance sensor inside a fridge. The thermometer data stream can be used to visualize if a proper temperature is maintained inside the fridge. If the temperature rises to exceed a critical mark, we use the distance sensor to check if the fridge door has been inadvertently left open and display an audio-visual alarm. Basement. A facility manager must regularly inspect the basement to investigate malfunctions and perform repairs. With an increasing number of devices and IoT sensors installed in the basement, the facility manager would like to know which devices are nearby, what their types and capabilities are, what the devices are currently doing, and what they've been doing in the past. Device information and visualizations of the sensor data and other event streams over time are shown as AR visualizations, spatially registered to the reference points. In this example, we demonstrate how IoT visualizations are generated automatically from existing infrastructure and its documentation. Mopop. This example interweaves analytic work with physical manipulation of a large number of passive references. Inspired by the Museum of Pop Culture, we created an application to design an exhibition room showcasing the evolution of two music genres. We re-implemented Stream within RagRug to showcase a complex visualization workflow. In this example, users can link together 2D scatter plots to form a parallel coordinates tree. Data within the scatter plots can be filtered through a tablet interface, which is synchronized in real time across the network. Using RagRug, we could mimic the original application with very minor visual changes, while drastically reducing the original implementation's complexity. Control AR. Control AR is an AR visualization system for MIDI devices which supports musicians in the use of a keyboard instrument. In the original implementation of Control AR, 2D visualizations generated by a static display are overlaid via a halfway mirror on the keyboard, so that the visualizations are registered with physical buttons, sliders, knobs, and other input elements. Our re-implementation of Control AR uses RagRug to gather, process, and visualize data generated by a MIDI keyboard.
Okay. So I hope the video played all right. I'll share my screen without the video optimization now. So, right. So you've seen some examples of what we can do. Now, what is the scope of these things? I would like to start with discussing a traditional visualization pipeline. So we see what our starting point is. How are people doing visualization with software systems on the desktop today? Yeah? This is usually expressed as a pipeline where you start with, I'm calling a virtual model here. So this is just some abstract data, which is then visually encoded or visually transformed into a visual representation. And then it is rendered. And the result is shown on a display and obviously perceived by the user. And only that last step, the perception, is where the physical world comes into play, because the user is actually looking at the desktop monitor or some sort of viewing device. Also, the user will have the ability to interact with the visualization somehow, but this interaction is necessarily abstract because it's only interacting with this abstract data in the real world. And that encompasses the whole range of visualization flavors or applications, be it sort of mostly passive visualization where not a lot of interactivity is going on, or visual analytics where you're trying to drill down and apply sense making through a more elaborate procedure, or even authoring where you're creating new visualizations, new data representations. All of that is the state of the art in traditional visualization. And now if we move on to immersive analytics, really only one thing changes. The conventional display is replaced by an immersive display. And that brings about really interesting properties which are now explored by quite a few people, such as increased spatial understanding, get more depth cues, or the possibility of having this decreased information clutter because you can have a very large virtual display now. You can support peripheral awareness, at least if you have a good VR headset, let's say, that has a wide field of view. And in general, we can assume that there's a higher information bandwidth because you can just show more data, more pixels. And so as a result, you get immersive perception, or call that spatial perception if you want. You get immersive interaction. You can have, for example, if you have a hand tracker, then you can grab the data, the visualization that is in front of you rather than having this indirection by using a mouse. But in the end, everything is still virtual. So even in AR, all data is abstract. This can still be very compelling. I'll just show you this really nice work, IMAXIS, also from the Monash group in Australia. Let's hope this YouTube video plays.
In this video, we present IMAXIS, immersive axes as embodied affordances for interactive multivariate data visualization. IMAXIS uses the manipulation and assembly of axes in a virtual reality environment to create and explore a variety of rich three-dimensional data visuals of multivariate datasets. IMAXIS is a modeless visualization system. The axes embody affordances to create visualizations given the attributes they represent.
So we really don't have to discuss that a lot now. You see it's a three-dimensional world, but it contains very abstract visualizations, which are now embedded in sort of a virtual space. That's immersive analytics. And now, if we go to situated analytics, if we draw up a situated analytics pipeline, then several things change. And I'll start with the perceptually situated display. So obviously in AR, we can show the virtual and the physical at the same time. And so suddenly physical reality plays some kind of role. And this perceptually situated display goes beyond a pure immersive display by not only showing the abstract or otherwise imperceptible data, but displaying it in a way that is embedded or blended with the real environment. For example, if you have a see-through head-mounted display, an optical see-through or a video see-through mode, then you see both the real world and the overlaid data or the registered data at the same time. But that's not the only thing that changes when we go into situated analytics. We also have the referents. So the referents, of course, bring about different physical interaction capabilities. You can now do things with physical objects in the reality, but before you could only, point towards virtual data elements or maybe shoot rays in the environment. But now you can physically touch things. You can move furniture. You can open a cupboard lid. You can sort physical things and so on. But besides the importance of physical interaction, referents also establish a physical context. So in order to get that context, of course, we need some sort of sensors that let us sense where passive referents are, or if you have active referents, such as smart devices, they will broadcast over some IoT channel what they are doing or what's going on sort of voluntarily. So this idea of tapping into sort of a networked physical environment is not unique to situated analytics. It's actually what ubiquitous computing is all about. But now with augmented reality, we can afford a much more fine-grained spatial interaction. And the third box that is highlighted here is the physical virtual model. So that's another unique thing in a situated analytics scenario. We require a model of reality. We must have at least some kind of minimal model of the relevant aspects of reality. Otherwise, it doesn't make any sense to, talk about the reference or put something in a real context. Yeah? And this, if you go back to the original definition of mixed reality in the mixed reality continuum proposed by Milgram and Kishino already in the 1990s, right? They don't only talk about how much you're mixing physical and virtual, they also talk about the amount of world knowledge that is available. So it's not only for the output, for the display side, it's also a model for the input side, except that this part of this very well-known work is almost always overlooked. Yeah? It's not the only mentioning of a physical virtual model. There's this work from the parallel systems pioneer David Gallant, the Mirror Worlds book, also from the 90s, or anything that has to do with digital twins that is now happening in industry is basically an embodiment or an outgrowth of this idea that you need a model of reality that is consistent with digital model that is consistent with reality. When these models grow larger and more complex, then of course you run into these typical big data issues. So if you just ask the big data questions that I'm sure you've heard before, applied to reference, we have the volume question. How many references are there? Many reference. How many different types of reference are there? That's the variety or the velocity. How fast does the data come from the sensor and the event streams? That may not be a big issue if you have a toy model like some of the examples that we will be showing you, where you have a handful of sensors. But of course, then when you go to a power plant or factory, thousands of them. So the physical virtual model is really also an important aspect that we would like to handle in RagRug. And that brings me to the research challenges, and I've enumerated them here from 1 to 6, and they tap or they tie into some aspect of this situated analytics pipeline that repeated here for your convenience. So the first question would be very basic one. How do we deliver visualizations in VR or AR? How do we drive a perceptually situated display? And the second question would be, how do we create a visual encoding or visual representation for VR and AR? And the third question would be, how do we make visualizations aware of the reference? And another term of saying where is context aware, context awareness. That's the terminology that is coming from the IoT or ubiquitous computing community. But it's the same question. Now, the fourth question is, how can we create a comprehensive physical virtual model? And the fifth question is, how do we make visualizations reactive to changes in the real world? So when something is sensed in the real world, something is happening to passive or active reference, how do we learn about it? And the sixth question is a very broad question, but I've tied it to the user here because it is about what the user can do. How do we support the user in the situated authoring of visualizations, the creation of new applications that make use of that situated analytics infrastructure? These are the 6 questions that we will try to address today, and that are for which we have developed RagRug to have some sort of tool that lets us work these out. And I'll start, of course, with a simple one. The first question, how can we deliver visualizations in VR, AR? Well, the answer is completely underwhelming. I really have to stress that. We'll use a standard approach of deploying the Unity game engine for real-time 3D graphics, and then piggyback off all these great VR, AR, XR toolkits that are integrated with Unity. No commercial vendor today can afford to not support the leading game engine because they want to make money with VR, AR, XR games. And so that's what everybody is using. Yeah? Collaborative features are theoretically easy to add, but I will not talk about that now. There could be alternatives such as Web3D and WebGL maybe, but then you can't really beat the Unity ecosystem, in my opinion. I hope I'm not insulting somebody here. There are the proponents of the WebGL sort of train, but we've benefited from this largely free, at least free of cost software infrastructure, and that's what you see here in the bottom as a little software stack, right? You have your VR AR hardware, you have Unity, you have these vendor-specific libraries such as OpenVR, RTK, and then you build your application on top. Yeah? So that's, again, completely unsurprising. Now, what you may not be familiar with is how you create visual encoding for VR, AR, and here we're also not inventing anything new. One of our mottos was, do not reinvent the wheel if there's a good wheel out there. So we take one state-of-the-art implementation, IATK, the Immersive Analytics Toolkit, which basically, if you look at the software diagram, is now sitting here in the middle. It's using Unity for rendering, but it has its own way of creating the graphics. That's called the grammar of graphics approach. It's basically a procedural decorator pattern that everybody in the visualization community is using. So if you go to the web and you look at web visualizations, such as the ones created with, say, D3, that's one of the market leaders in that space, it would be the same kind of grammar of graphics approach, the same kind of procedural encoding with minor variations. In the case of IATK, it's nice. It nicely scales for fast rendering via its use of geometry shaders. So that's one of the tricks that they have. Authoring would be done inside Unity using conventional C#. And then the interaction is relatively basic. So it's nice. You can do 3D brushing and stuff like that. But in general, the interaction capabilities are really not the strong point of that. But the visual encoding is extremely useful, and we're relying on that. And again, we're not doing anything innovative there. So now our checklist with the 6 requirements. What Unity and IATK do for us is address these question 1 and question 2, deliver visualizations and create visual encoding. What do we do with the remaining 4? That's going to be the question for the remainder of the time that I'm filling here. And I'll start with the context awareness. With the third question, how can we make our visualizations context aware of the real world? Well, let's look what people in the real world are actually doing. And I'm referring here to the sort of community of Internet of Things developers that have to find solutions for coordinating and controlling lots of sensors and embedded systems and so on. And the dominant development paradigm here is having some kind of data flow architecture where you have event passing in a graph, a pipes and filters type of setup. So the data flows through the graph, and in every node it can be manipulated. And this pipes and filters programming paradigm is, of course, very popular as a visual programming metaphor, and you get these kind of interfaces such as shown on the right-hand side here, where you have these various nodes, and then you can use a conventional, graphical user interface in a web browser even to create those node link diagrams, write a little bit of custom code in a scripting language, and connect that to data sources on the network, deploy the whole thing, and you have your interactive distributed things application. And a major platform in that space is Node-RED. So Node-RED is an open source framework for Internet of Things that is out there, that is professionally used in industry, also widely used in home automation, enjoys a very large user base. It runs in a typical server infrastructure based on JavaScript and Node.js. You see a software diagram of a typical Node-RED framework here on the right-hand side. And it would consist of Node-RED, supported by JavaScript and Node.js, then it connects to an HTTP server, so it can deliver all kinds of user interfaces, and one of them would be for visual programming user interface. That's the screenshot that I showed you just beforehand. It also connects to a publish subscribe network. So that's a I don't have time to go into details here, but publish subscribe is basically message passing with a topic organization. So rather than sending directly to a recipient, you publish information on a particular topic and everybody can subscribe to that. So it makes for very flexible, easy message passing coordination. And then various databases are attached, which we shall be using for storing the physical virtual model. So all of that, again, is nothing proprietary. It's something that people are using in that form that is shown in the software diagram here for professional and large-scale Internet of Things applications. But of course, it has nothing to do with virtual or augmented reality. This is the interfaces. If there are any, if it's not just automation, if there are interfaces, they would be some kind of web pages that are delivered via HTTP. Now, let's jump ahead and put those two things together. Node-RED on the left-hand side, IATK on the right-hand side. An MQTT, an IoT device on the bottom would be the starting point of a visualization pipeline. So let's say we want to visualize readings from a sensor on in some sort of AR application. What would have to happen? Let's follow this pipeline. We'll start with the IoT device, giving some data. This is already covered by sort of this Node-RED infrastructure. So the data goes into Node-RED, for example, via the MQTT protocol, is somehow processed there. So that would be in visualization jargon, this would be data processing or pre-processing. Then this data is forwarded again over the network to what I call an IATK or AR application here. So this is the client that would run on some tablet or headset device or whatever you have. There the data goes into IATK. For that we will need some sort of networking library. So we're using an MQTT library here. That's nothing very special. And then IATK does the visual encoding, passes the output to shaders in Unity, and the rendering happens, and you see the result in your VR or AR display. So that's great. We've put these two underwhelming existing platforms together, and we've gotten a lot of value out of that. It has good expressiveness. All the things that we would want can be done, but the ease of use is really just very mediocre. Now you need to learn these two big platforms, which their own quirks and pitfalls, and that's not what we were hoping. We would like to have something more powerful and more elegant. So let's look at our checklist again. We can now not only address Q1 and Q2, but also Q3 and Q4 basically via Node-RED, because it gives us this context awareness via its connection to all the sensors, and it supports all these databases where we can put a physical virtual model. I mean, it's not free of effort. You still have to create the data, but at least you can store them in SQL or in some non-SQL databases, time series databases, and so on. All of this is deployed with a single invocation on, let's say, container orchestration like Docker. What's missing is this elegant integration. This is what is addressed by the questions 5 and 6. We want to make the visualizations reactive to the changes and the real world, and we want some powerful authoring. So how are we going to do that? Well, in order to get that, we have to make a variant of the software infrastructure that I've shown you before, where again, on the left-hand side, you have the unmodified Node-RED infrastructure, and on the right-hand side, you have slightly modified IATK Unity infrastructure. And we're doing, we're making 3 extensions, or I call them 3 steps here. So the first step is we extend IATK to support a reactive programming model. And What that means is that when new data comes in, visualizations automatically update. That's not, you would think that this is logical, but that's actually not the case in most of the visualization systems that are out there. The data is static, it's loaded at the beginning, and then you can manipulate the data, but no new data can come in. Now, we've created an extension that we call reactive IATK that solves exactly that problem. The data that IATK consumes is considered volatile, and whenever some new data comes in through the data flow, then the visual encoding of that data is rerun and the visualization is updated. And the second extension is that we enable the same data flow that Node-RED understands internally when it runs on the server based on Node.js to also run inside Unity. That sounds a little daring. Actually, first you need to add JavaScript support to Unity to replace the C# layer, or to extend the C# layer, let's say. Third-party tools for that purpose exist, which we're using, and work surprisingly well. And now that we have this JavaScript support on a language level, we can write a Node-RED compatible data flow scheduler in JavaScript with a very small amount of code. Because what is done, the core of Node-RED, so to speak, that is, as you see it on the left-hand side here, is really inside a JavaScript environment, namely Node.js. It is able to interpret a big JSON file that sets up the data flow graph and then schedule that. And we cannot run Node-RED itself inside Unity, but we can make a clone of the Node-RED scheduling that's fairly easy to do, and run that inside Unity. And so as a result, you can now use the Node-RED-like JavaScript data flow everywhere throughout the entire system. And then the third step is the connection, which is basically the tip of the arrow going into the bubble number 3 here. You have to connect the data flow to reactive IATK. And now the whole pipeline from 1 to 2 to 3 to 4 can all be expressed with a uniform Node-RED-like data flow. That is an umbrella for all the subsystems that we've seen so far, and they can all be programmed using the same kind of data flow with mixed with some JavaScript statements. So that's what is now often called a low-code environment, an environment that is suitable for sort of unexperienced programmers, but also convenient for experienced programmers because it's very forgiving and very flexible. If you remember question number 6, it was about how can we do situated authoring. Well, we first have to say what situated authoring is really about. Situated authoring is about creating the visualization at runtime and instantly reacting to any particularities of a physical environment that you might find when you go there, or as suddenly something happens, you change a bit of the system code if it's not already automatically adapting to the changes. And these kind of capabilities for situated authoring are already solved by the measures that I have just introduced. So first of all, we have this uniform programming model, data flow everywhere. Actually, if you look more careful, for those who are interested in that kind of thing, it's the formalism that we fulfill with our programming model is event-driven functional reactive programming. So that's actually a version of functional programming that is known to be very efficient for distributed systems, and that has also been other visualization systems for the desktop before. It makes this, this is confirmation that it makes a lot of sense to use this formalism. It has been used in other powerful systems before. And the reason is that it supports authoring very well, in our case, situated authoring. Second is we have existing interfaces for the programming that are also encompassing visual encoding. So we can use the Node-RED style programming now applied to IATK visualizations. But also we have these interfaces for managing databases and such that are already part of this Node-RED infrastructure. And the third thing is that JavaScript, of course, allows hot loading, right? It's unlike C#, which still requires an explicit compiler invocation. JavaScript can be loaded and reloaded on the fly. So you type a line of JavaScript code, press a button, and it is loaded into one node of the data flow, and then the behavior of the system changes. So you typically don't have to shut this system down. We just keep tuning the nodes that are in the. It's like an operation, a light operation on an open heart, right? While the heart is beating, you're changing the circumstances here. This is what can be done with JavaScript, and would be much harder with even with C#, despite the fact that it's a bytecode language. So we get the situated authoring as well, and that means we've addressed all these requirements that we had, which is actually quite a lot in terms of a breadth of support. Nice observation here, and this is actually my final slide today, is that a lot of this is for free. So it sounds complicated, but it was more a question of finding the right concepts and right tools and putting them together in a way that nothing stands, there are no obstacles. The actual implementation effort in terms of lines of code that have been uniquely added is relatively low for a system of that complexity. And I'm reminded of the Bremer Stadtmusikanten. So this is a fairy tale from Germany. I'm not sure how many of you are familiar with this kind of thing, but it's really just the idea of ride along. So animals, in this case, a donkey, dog, cat, and cock, team up to fight an enemy, a bad human. And they do that by riding on top of each other. So this is what's going on here. I've roughly labeled the software infrastructure on the right-hand side of the animals that we're using here. What we wanted was have lots of powerful features, have a unified programming model for it all, not reinvent any wheels, at least not the big ones, and also, and that's actually a hard challenge, only use existing tools with a strong existing user base, not use any obscure open source libraries, which are then discontinued next year. And so your whole software ecosystem breaks because somebody else is not maintaining their software. Of course, that could still be the case for any one of the tools that I'm mentioning here. But we are very confident that these are solid choices. And so in the end, it's possible to have all of this at once. You get the sort of aggregate effect, the aggregate weight of all the big animals here. And you get it with a really nice programming interface that lets you do immersive analytics, but also situated analytics with or without the Internet of Things. Lots of open avenues here, and we believe it can be, or we hope it will become a widely used tool and a sort of unifying ability for many of these experimental works that are out there right now, because many of these research projects that we read papers about, they are relying on Unity, but then the interaction programming is sort of proprietary, right? And because of the big the powerful features, it's very easy to run that inside something like RagRug, and you're not paying a penalty, maybe apart from a very minor learning curve at the beginning. Yeah, so that was my part. I hope I've whetted your appetite, and I guess we can have a few short questions maybe now, or you let Phil move on, give you concrete examples, and we do more questions at the end. immediate.
May I ask a question? You mentioned that actually what is kind of an issue is that you have to learn Unity and you have to learn Node-RED, and now you integrate Node-RED into Unity and you still have to learn both kind of technologies. Did I get this right?
Well, you will have very little native Unity programming to do, right? You don't have to touch C#, for example. Only one programming language, JavaScript, in a lightweight version, because you mostly do this data flow clicking of node link diagrams, and then write little bits of JavaScript only if the default nodes or the existing nodes do not suffice for what you're trying to do. Yeah? Many of the standard examples can be put together with off-the-shelf nodes that are either shipping with Node-RED or with our RagRug sort of inventory. And then when that's not sufficient, you write a little bit of JavaScript code, which I believe can be said to be, well, easier than doing, let's say, heavy-duty object-oriented C# programming. Also, the IETK insulates you a little bit from visualization generation, because it comes with a rich vocabulary of visualization marks and visualization styles. Yeah? Although, I mean, we just had this discussion the other day where Phil wanted to do it wanted to solve some problem with standard IETK tools, and I wasn't satisfied with the visual look of that. So then you have to go a little deeper. But it's all wrapped in JavaScript. These are, high-level tools. And yes, of course, you have to learn the tools that you're going to use. But compared to learning the native tools that are all listed here on this slide, and then putting something together on your own, I would say more than 50% of the effort is probably eliminated or taken care of by you. And I'm not sure if Phil will have time to cover this today, but we had this one example where we re-implemented a system from literature called Stream. That was a paper at Kai 2 years ago. And we actually did a side-by-side comparison. 50% of the code was eliminated, right? The proprietary solutions that were in this original Stream implementation could be done out of the box with RagRug. And it wasn't even tapping into, I mean, the Stream system is a pure immersive analytics system. It has no reference and no Internet of Things. If you do that, then of course you would have even more legacy to cover. And so I don't think you get a better bang for the buck, so to speak, from anything else at the moment. That doesn't mean it's zero learning effort, of course.
I will give some insights into that right in the beginning.
Yeah. Now, just one more question. I'm sorry I have to leave early for another workshop. Well, I will present the paper that it's actually very much related to what you are presenting, but my question targets this already. Because as I understand, IETK is like the basic vocabulary that you have for visualizations in RagRug. That means, like, simply speaking, classical charts and graphs and these kinds of data visualization. But what we did in our paper is we also like to have some, indexical visualization, like visualizations that directly relate to the real model, like what you mentioned as the physical virtual thing here. What would be necessary to achieve something like this with RagRug? So if I would, what we did, we had an industrial machine, an aluminum furnace with a huge pipe system, and we overlaid data coming from the industrial IoT system over this. That would probably need some customization for that.
So
the bottom, I mean, it doesn't solve the actual problem for you. It just gives you sort of the comprehensive tools. In this case, if you want to raise the visualizations with machines, for example, it's actually something that we are very interested in. Typical assumption is that you have some kind of CAD model of the machine, or at least a 3D scan. I mean, the information has to come from somewhere. But then you can not only throw it in one of the databases, but in this case, we also have some tools that I didn't talk about to pass the CAD models and generate registered visualizations or visual glyphs based on CAD data. Again, that expects that you have a CAD model that is sort of a standard format, and you know how it is structured. All of this information will have to be provided by you. But the effort of, you know, if there are any Python programmers in this audience here, you know, you get lots of high-level libraries, and it's a few lines of code. The same goes here. For those common kind of problems. IEEE doesn't do that for you, but the tools for, well, the database itself also doesn't do that for you, but the tools for filling the database and harvesting the database will do that for you. And if such a tool doesn't exist yet, you would have to write it for your particular use case. Well, we have some, but others may be missing. But at least we hope that there can be some de facto standard, right? If this is a useful tool and a useful format of putting stuff in the physical virtual model, then you probably want to reuse that or reuse somebody else's solution. And it's not completely proprietary if this is embedded into some. The typical thing we've seen is a Unity application with some text files from where data is loaded. And that's that's
sure.
not cutting it.
But the question's answered.
Yeah. You can probably go to one of these CAD vendors for Unity. There are professional converters from CAD to Unity, but these are expensive. So
well, we tried some, but still we weren't really. Yes, they actually, the amount of work you still would have to put into it made us actually remodel the whole thing by hand, because that was quicker and also much more customizable.
Yeah. All right. Well, if there are no further questions, then maybe let's give Phil a shot. Phil, do you want to take over the screen?
Yes.
And I also have to leave because I have to jump into this open source software workshop now. But Phil will be happy to answer all your questions. So thank you.
Okay. Can you see my screen already? Okay. So that works, right? Okay. Okay, great. So there is an overlap to what Dieter talked already about. So I will just fill in some gaps and then go directly to the examples. As I understood, we have time until 30, right? Okay, okay, great. Yes, I will. So you saw already that. So the whole continuum where we are talking about maybe a takeaway message here. There are like these browser-based tools here in orange, and then we have the Unity-based tools here in green, which are fairly recent, like in the last 3 to 4 years, and they mostly follow the same principles of this whole visualization decoration. And then we decided like to go with IEEE, as you already heard. Yeah, grammar of graphics, we had that. So it's already on GitHub, and the slides will be there too if somebody has to leave earlier. And there are like far more slides as we can fit into the 30 minutes. Again, this short overview, maybe a detail that was not mentioned in particular. We have support for this whole stack of databases like InfluxDB, which is a really fast time series database for real-time data, and CouchDB and relational stuff like Postgres, or you could also use MySQL or stuff like that. And this is all connected to this whole flow system. So these are the 3 images of the examples that we had. The one is the basement at TU Graz. The second one is the stream application, and the last one is this control keyboard. All of them were compiled, not compiled, but built within a flow, and they use the same application. So maybe in addition to the last question, we only compile the client once and can switch at runtime the applications that we write in JavaScript in that form. We saw that already, so I will focus mostly on that part down here, the application itself, and how we write apps for that. Yeah, we heard that already. We saw the video. Okay, Node-RED. So it offers you a front end to the backend where you can just click together a UI. And what is also nice here is that button clicks here can be translated into messages, and these messages are forwarded to any client, in our case, the HoloLens client. So you can easily implement like a second screen scenarios or adjust visualizations or just by a nice UI for that. Yeah, what else? So this is mostly overview. Yeah, so we have one key point, modeling the world. So usually the referents are some pieces in the world, like there's a smartphone that is placed somewhere, and we have a number of different options here how to model that. To model that. So one thing is that sensors can use this topic structure where all sensors, for example, in a certain location within my application, serve data on. And this allows us to, without any effort, just have a client which subscribes, for example, to a top-level hierarchy of this topic and receive all the data. Or we can use wildcard stuff things that gives us like a certain choice of sensors that are around. And this is like a really nice enabler to do like data discovery within a certain location. And this also gives it a nice pattern where we can just operate on the data itself. For the examples that we used, we follow a pattern which is like we are in a building, we have a floor, there's a room. In the room, there are devices, and the devices have parts, and every part has like an ability and it sends data. So this means that in my phone, there's a temperature sensor, and the temperature sensor reports the temperature. This is what we are trying to mimic with that structure, and this was used among all the examples that we have. We can also localize within the world using, for example, the Azure anchors, and this works over a SID or a basic detection, for example, of the Wi-Fi. So which allows us to just walk into a room, detect the Wi-Fi, and then instantiate all the world around and make it interactive. So this is mostly a bootstrapping part of the application, but as soon as we go into this physical world modeling, then we need some mechanic like this. From the example that you saw in the video, we created, so this is the mop-up scenario where the user can pick up a record, detect it using Vuforia, hang it onto a wall, and then it creates like visualizations which are done via simple lines and colors, and also visualizations that are done with the IITK part on the right here. How we model that is that we have a big database of all the records and artists, and we also have a 3D representation of the world that you see in the top right. And our modeling of the virtual world is registered onto that and allows the user to have this in situ interaction capabilities for that use case. Again, this whole example was implemented using this flow graph. We already saw that part of the video. This is just an overview of some features. So CouchDB is like a huge horizontal scalable database that can hold just a lot of document-based data. So simply speaking, we just store JSON objects inside there and can access them at runtime and manipulate them. So this gives us sorry, a nice handling to overcome this whole in-app data management part, which I'm sure all of you know. If you have like bigger apps, it starts becoming a mess quickly. The AR client, let me just give a short overview. So the motto that we follow is we compile the AR client as a framework, and it can execute JavaScript code. And in that form, it allows us to have a really slow moving augmented reality client, which runs on the HoloLens. And then we can just throw implementations on top of that. And only if we add a new hardware feature, for example, like we use some sort of tracker or some other C# library that we don't have already included, then we have to create a new build. And this makes development of such scenarios and applications really quick. Here's again the stack. So one part is Power UI. This is an open source JavaScript interpreter for Unity implemented in C#. And what it does for us is it automatically does all the binding. So you can write JavaScript code, which will include Unity code. So you could write inside the node JavaScript command that maps down to C# commands like new game object, and then you would get a new game object, and you can inject that code without any compilation. So this is already a huge benefit. And then we have both paths open. So an application can either live in the Node-RED flow world, or you can do it old school way and write a monolithic JavaScript application, or it can be like a mixed version of that, where I also have an example for that. Yeah, what else do we have? Yeah, it follows this whole web principles like fuzzy loading and lazy loading, hot plugging. So for example, you can add a function to your JavaScript context like payload injection, and then you have enabled a new feature on the client. I hope this is not too technical, but we need some basics of that to understand how these applications are done. The default loading procedure is very easy, more or less. So we have like a configuration which defines the endpoints. So this can be anywhere in the network where we can reach it. This is loaded through the C# framework, and we use a common entry point main.html, and this one keeps then loading up more and more stuff. And we have a runtime, which is a collection of nice and handy shortcut functions to do all sorts of stuff in Unity, like parentship and destroying of game objects and all the stuff that you need if you would write a Unity app. And this makes it like in a really useful form. We have a white label application, main.js, that can just load from the database and spawn some demo visualization. So this would be already a good starting point to look into it and try stuff out. Then we have CNR.js. This is the interpreter of the flows in Node-RED. And there is no limitation theoretically on how many you can have from them. Obviously, HoloLens is not that capable like a newest iPad generation from the computing power. And then we can use libraries like jQuery to make our life easier. Yeah, you will find all the code in the HTML UI part in the RagRug repository. And as I said, this gives us shortcuts, for example, to create a new ILTK visualization that we can then fill up with data. It also gives us access to low-level device capabilities, like enabling the torch or starting some sort of tracking or access camera images and so on. And it follows a principle of macro style functions. So it can be extended at runtime, but also used as is. So you might already get the idea that this is like very flexible, and it gives you a lot of different opportunities how to implement stuff. Yeah, the main.js has also a nice feature. We can load asset bundles. So Unity's compiled contents asset bundles, which we use to load any sort of 3D models in that manner. And this can be used at runtime, and we store them in the database or at the file share and you can just load them at runtime and use them up. So there's no need to put them elsewhere also. Yeah, and following with the client-side interpretation, for example, you can write a flow in Node-RED, which will execute simultaneously on a server, but also on the client. And there you might want to do some sort of routing of your content. So you can write, for example, a filter very simply and just check if some feature in the client is there, and the messages will be passed that way. We have a basic support for the most common nodes in Node-RED, like MQTT, inject, debug, function. Yeah, these are the mostly used of them, and we plan to improve on that part. Now let's dive into the tutorials. So I have like I will present a build up from example to example. So let's start with the IITK. So this is like without any heading. Yeah, as already said, you have an editor where you can drag in your data and then you can configure it, and you would deploy an application or run it in the editor, and then that's it. What we can do is we can write a JSON file. I will come to that later in detail. And this JSON file is passed into IITK, and this creates us the visualization that we want to implement. So in that case, the flow is downloaded on the client. The client executes the flow, checks for the definition, the JSON-based definition for the visualization, and then creates an IITK instance and then shows the visualization. To understand all these settings presented in the editor by IITK are mapped to a already implemented by IITK JSON structure that we expose. And this structure can be used to create a visualization. But what is also more fun to stay within this data flow context is that we can mimic parts as data flow for that configuration. And this means we have either an editor version or this configuration, which will produce the same JSON output, which gives us the visualization. So the smart fridge is the first example that you saw. It has no location, and it uses the data flow in that case to implement its visualizations. So the task was to make the fridge smarter. When you open the door, you should see an alarm. When you close the door, the alarm should end, and you should see a visualization of the temperature and if the alarm is triggered on or not. We used a tiny ESP sensor together with some ultrasonic distancing and the temperature sensor, and put that with the battery bank into the fridge. So once you open the door, the distance will be increased from the measured from the sensor, and then the data is reported accordingly. Yeah, some requirements. We want like a really simple XY visualization, where on the x-axis we have the time running, and on the y-axis we have either the temperature or the distance. Yeah, and the alarm should turn off once somebody closes the fridge. So we have like two distinct flows for that. All the examples are in the GitHub, so you can have a look in detail into that. So this top part creates the right temperature scale, and this lower part flows, so they look very similar, creates the left part for the distance. And here you can see on the bottom right how the sensor is put into the fridge. So this is a very simple test for that. How to set up the visualization? You just create a node, put in this JSON structure, and then you can use all known abilities of that, like which kind of geometry, which axis, where does the data come from. And then we have this template part here in Node C. which just gives you exactly that based on that configuration. So this comes already with the toolkit. And by using that part, the visualization gets spawned. And it does like stuff like create a blank visualization, put it somewhere, make it, for example, hand draggable if you want that feature. So you want to place it somewhere, then you add some dimension over there, and you can apply the configuration that you created. And at the end of this node, you have the visualization. Again, as I told you, you can write Unity code inside JavaScript. This comes with the bindings. For example, you can access the game object, that's a hook in the camera view. Then you can access its transform, and you can access its position, and it will give you back a position object, a vector 3, as it comes with Unity. So this comes really handy. We can enclose that into a try-catch block, and then we can also execute this code on the server side if we have to. So this could have like 2 parts inside of it. And this is how we check that it's only executed on the client side. Yeah, and the lower part just takes in 2 data sources because the sensor reports data on both topics. So we can access the data from the payload, how the sensor ships the data here on the right side, and just add it to the data that way. So this is very common in the IEEE examples for that part. Yeah. And finally, the code within the client, we can, for example, create like a button to load that, or we can do that automatically. And in this case, we only define which flow we want to load on the client, and this flow is then instantiated in front. So this is another video on that. The fridge is instantiated. We have these 2 visualizations over here. And once we open the fridge, the alarm shows up, and the data changes over there. So, yeah, so this was an example without any particular location at site. The 2 visualizations were placed by hand, and now we can have a look into how we would set up a location. This is not exactly necessary, but very helpful for larger, I would say, scenarios. We propose a structure, so it's free for you to end that, to change the structure. We have like a named SID within the database, and then we have a list of devices, and every device has its own document. And this document might be hand generated, but it also could be automatically generated. For example, a part of the question was this cut model thing. We can, for example, pass STL files with the offset pipeline, and then get as inputs if needed. But this is like not covered by these tutorials over here. For localization, we can also store the Azure anchors within the database. So no matter which HoloLens you would use where the app is running, it would be capable to localize within this location, since it can download and process these Azure world anchors. The location setup is pretty simple, more or less. We have a main location document over here. We can add stuff like tracking information if you want to use Vuforia tracking, and we can add some names. And on the right hand side, we see the list of devices, which are in that case a simple list, which are also downloaded at runtime. Yeah, and on the right hand side, we see how such a device would look like. It has, for example, what parts are there and where is it in the world. And based on that information, we can spawn it when we detect, for example, a new location. We have an addition over here to load additional content. For example, this device would load a MIDI HTML file, which might again contain another set of JavaScript files or so. So we have many hooks in place to solve some specific problems for that part. Yeah, once you detect this location, everything is loaded from the database, instantiated, and then it's up to be used. Yeah, we can also enable, for example, 3D or 2D tracking with Euphoria. And there are also some examples further in the slides. Now let's go into the basement. This might be the more interesting example over here. So the basement covers data flow generation for visualizations. It adds the visualizations and it uses location to localize where the sensors are. What we had to set up to make that work is we had to define the devices and we had to register the devices within the world. In this case, we used just drag and tap to drag gestures and then stored their location after the HoloLens was localized within the scenario. We also had different sensors. For example, this black box on the cable is a combined temperature and humidity sensor. And we can implement proxemics since we know the location. So by moving closer to sensors, they will show more detail, and by moving further away, they will just collapse and then stay there as a view. So how this loading procedure looks like. So what we get from the HoloLens is a location within the 3D model. This loads then the whole area and the devices creates like this tag with all its values. It creates a visualization from IETK and it can render Grafana backend interfaces, for example, of historic data. In this case, also an arrow is implemented with a simple check. If the temperature is beyond 30 degrees, then show that it's getting warmer. It was summertime when I recorded it, and it had for real 35 degrees in the basement. So it was kind of hot. Here we can see what parts are loaded. So this might be of bigger interest in particular. So we see that the charts. So every device can load up such a chart based on this flow that we set up. And over here on the left, the violet one that says hallway with the hashtag at the end. This one connects to all sensors and retrieves all the data. And this allows to create, based on which sensor you are, specific data for each sensor. So this makes it very nice to write one bit of code that is generic for all the sensors, for example, in the environment. The blue parts over here, they are loaded over label.js, where you can decide more or less how much monolithic code you want inside there. And then the overall device with its components is loaded via the device file from the database. And within this definition in the database, we can set up, for example, Grafana links to add Grafana data over here. So I'm not sure how many are familiar of you with Grafana. This is just a backend tool to visualize data. So in this case, we visualize real-time data, which also runs on the backend. So since we could stop here if you want to ask some questions, or I can continue with some other examples. I don't know, however you feel. Are there any questions right now? Well, then I will, yeah, please go ahead.
I have a general question regarding IETK, but I don't know if this is the right point in time to ask this.
Feel free.
So I've been looking at IETK in the I think some weeks ago, and my impression was that it is at a I think prototype stage where it and without continued support. So do you have any knowledge of if and how it will be continued to be developed, or?
So we were in contact with Maxime Cordel and his student, I think Daniel Harris. So there is also a pull request from me to IETK, since we had to do some changes to it. And we also had to add this whole data source thing. Yeah, but this is not that critical, I would say, because every addition that we did to IETK is more or less general to any other visualization toolkit that would come. So before IETK, so since this is like a ongoing project which started like 2 years ago, we used U2Vis. So this was a paper from, I think, 2019 or so. I'm not sure. And we could just drop that out and drop that in and drop IETK in. So this had like little effort, since you only have like to provide a certain, I would say, convenience function wrapper thingy that you can use. And then this is like an effort of, I don't know, half a day or so. So this was very straightforward to do. But what they achieved, so even if they do not continue it, the framework itself from IETK is very capable for that scenarios. For example, it was hard to find some good software for the HoloLens that you can manipulate in that way, and then this makes use of this whole geometry shader performance benefits, which makes it really usable on the HoloLens, even on the HoloLens 1. So yeah,
great.
There is also the Unity project in the repository, where you can just run the simulator in the editor and play around with that. But it also compiles, for example, for iPad and Android. Some parts might not work in that case, so since it's not the extensive focus of us for the devices. But if you want to do like a quick touch of that, I also have pre-built HoloLens applications on the repository. So you can just install them. They will do more or less nothing, but they can load from the database and they can run all the flows that you want to try. So for example, the control. So this example over here, so this was done by our collaborators at the Stuttgart University. They just received a compiled version of the HoloLens client, and they just implemented it with flows. So especially this image over here shows a prototyping stage on the top left, and then applied to the real world. In this case, we used a Vuforia marker to do the localization over here. Yeah.
Okay. Thank you.
Okay, you're very welcome. Yeah, so are there any other questions so far? Let's see, what else do we have? Okay, well then I would close it at this point. I don't know how sharp we are on the time, because any other start will take like a little longer for that. Maybe I will just show you some interesting stuff. So let's see. Yeah, so using Vuforia, so we have the ability to run any 2D based tracking and detection, and we expose all the hooks of Vuforia. So you can just write a node that exposes on track and then tracked and then hook in there. So this makes it very convenient to write code for it, since you do not need this callback mess inside C# anymore. And the other thing is we also support the 3D models of Vuforia, which work more or less the same. We just add a JSON tag and then you can load this model for tracking. Yeah, turned out it's kind of expensive to run on the HoloLens too, but works better, for example, on the LiDAR iPad in that case. So there's also support for some nice features, and we have included the mixed reality toolkit of Microsoft to enable all this tap, hold, and dragging and finger tracking nice UIs for interaction. Yeah, so I think I have covered mostly everything. Maybe also some interesting aspect over here. We have these UI elements in that part, which are implemented as an HTML page, and therefore you have to make sure that your mapping works right. So there are also convenience functions inside there to calculate the right size between real world and rendered HTML pixels within the virtual 3D world of the HoloLens, which is like always a thing if you want to do like screen overlays or something like that. So it's like it computes a one-to-one fit that your rendered pixels are on range with the metric unit system. Okay, well, so I think we have come to an end. Thank you for your attention. If there are any questions, I'm glad to answer them.
Will you have your slides available anywhere?
Yes, I will put the link on GitHub.
Oh, and please maybe also on Discord.
Oh, I couldn't manage to make them to make Discord accessible right now. I had some busy times with my little children.
Okay, if
but
you want,
I can send you an email with the link, and then
if you want, I can
process.
post it on
Yes.
on Discord, and as well as the link for your paper.
Yes, yes.
Because this is interesting. I have a student that is waiting to have access to your paper.
Okay, I see. I have also linked everything on GitHub over there, and I put the link in my profile. I think the profile is visible. I don't know.
I just posted the link in the Discord channel.
Oh, that's very nice. That's very nice. I have to upload the slides first.
Yeah. Okay, thank you.
But the paper is also linked in the GitHub.
Yes,
So,
I put, and I also put that under the YouTube video. So from whatever site you reach it, you will find the
okay.
stuff.
Thank you very much for your
Thank you
nice
for your
talk.
time.
It was very interesting. It's a very, very hot topic in my view.
Thank you. Thank you.
So
yeah, feel free to come back to me with any questions. So I'm very open to any sort of collaboration or advice or whatever comes along. Yeah. So we have right now a couple of students trying stuff out with it and improving some parts. So yeah. Okay.
So
thank you also from my side. Very interesting.
So Gabo, do you have a question, or was this a buy? Oh, this was a buy. I see. Okay, well.
bye bye.
Bye bye.